Hi everyone, this would be a great video for you to pause and try and work through. There's 2 pages worth of stuff on this problem number 4. So go through and see if you can, on both the graph of big F and the graph of little f, represent each of these things. So first one, f of a, second one, integral from a to b of little f. So walk through and see if you can figure out, you can kind of narrow it down to a length, a slope, or an area, I think, on all of these, if that gets you started. Okay, so f of a, we're given a is an x value. So for each of these, we're going to go say on the graph of f, what does that look like? On the graph of big F, what does that look like? So on the graph of little f, f of a is just your y value, so it's going to be the length of this line. On f of big F, what we want to remember is that big F prime equals little f. So little f of a is big F prime of a. On the graph of big F, that means that we're looking for a derivative, which is slope of a tangent line. Okay, so there's the first one. The second one, the integral from a to b of f of x. So on little f, again, usually it's easiest on little f. We hopefully know by now that definite integral is related to the area trapped under the curve f of x. For big F, this goes back to your first fundamental theorem, which says that this will be the same as big F of b minus big F of a. So thinking in terms of graphs, big F of a is this first height, big F of b is this second height, and if we want to know the difference between the two, there's lots of ways you can draw that, but I would say the easiest way is to say subtract that bottom height from this full height, and that is your big F of b, your difference between big F of b and big F of a. And this goes back to that net change description. If you integrate the derivative function, the rate of change function little f, you get area. Relating that back to the graph of the antiderivative big F, you get change in y. So the area under little f is equal to the change in y on big F. Okay, so now it's similar, but we want to divide what we get by b minus a. So part of this is just recognition. When we get over here, we want recognition that that is the formula for the average value of little f. So if I'm looking at this interval AB, this is going to be kind of a visual approximation. I'm going to imagine that if I flattened out all this area, that I would get a height. Let's see, I think it'd be pulled a little bit that way actually. Something like this. Oops, it doesn't need to go all the way over. Sorry, don't mind me. Something like this of a rectangle that catches the exact same amount of area that's under the curve. So this is definitely approximate, but that's kind of what I'm thinking. The average y value, that is equal to the average y value of little f. To figure out what this looks like on big F, we're back to our first fundamental theorem. We want a big F of b minus a big F of a over a b minus a. And that is absolutely a slope on big F. That's the slope of a secant line. So I want to take the point A, big F of A, B, big F of B, and I want to connect those 2 points with a secant line. And the slope of the secant line is equal to whichever of those two you're looking at.